Okay, so in the last lecture, I was trying to obtain recurrence relationships involving orthogonal polynomials. So what I did was I told you that I take a polynomial p and x. By convention, I can write it as kn x to the power n plus other powers of x, lower powers of x. Similarly, phi n minus 1 x is kn minus 1 x to the power n minus 1 plus lower powers of x. Now, if I construct another function from Pnx and Pn minus 1x, which is given by Pnx minus Kn x, Pnx, Pn minus 1x, then what happens is that this function is this function that I have here, which is the f of x, is a polynomial of degree n minus 1. Because as you can see, when I divide this by kn minus 1, then what I get is x to the power n minus 1 as the leading. Multiply by x, kn, then the leading term will be kn x to the power n. So when I subtract it, pn minus kn upon kn minus x, pn minus 1, the leading power, which is the x to the power n, vanishes. And so fx is a polynomial of degree n minus 1. Now we know that every polynomial, every function of degree p can be expanded in orthogonal polynomials of degree up to p. So we are p is equal to pnx minus kn upon kn minus 1x, pn minus 1x. That can be expanded in terms of orthogonal polynomials p nu from nu equal to 0 to n minus 1. So this is where I stopped last time. And now let us try and get expressions for alpha p nu. Alpha mu. I will take f of x p mu. Okay, if it is normalized polynomials, then this is going to be alpha mu is equal to p mu f of x. Take the inner product of this with respect to f mu. Use the result that p mu inner product is delta mu, so that I only get alpha mu. So what you will see is that because this function p nu is orthogonal to all polynomials of degree less than this thing nu, what we will get is the following. So you will see minus 1. So let us see how. So I have the following: the coefficient I will see that pn x minus kn x pn minus. This will be equal to pnx comma say polynomial pnx comma p mu and minus of kn upon kn minus 1. So if I take the overlap of this one with the product with p mu, then what I'll get is the following. So I don't have to have an alpha mu. Okay. So minus kn minus 1 upon kn x pn minus 1 of x comma p of mu. Okay. So because pnx is orthogonal to all polynomials, whether it is orthogonal polynomial or any polynomial of degree less than n, on the right hand side, goes to n minus 1. Okay, see this expression. Okay? So you see this. So here the summation is only going up to n minus 1. So Pnx comma P mu is always 0. So I will get goes to n minus 1. So the first term is 0. So what happens? Let us look at the second term. So this is Pnx minus Kn upon Kn minus 1 x Pn minus 1 x comma phi mu. So this is going to give me minus Kn upon K minus 1 x Pn minus 1 x comma phi mu of x. Okay, so I can write the following. Okay, what happened? X Pn minus 1 x phi mu x is actually integral a to b wx Pn minus 1 x x phi mu x dx. Okay, and what we have is this x p mu x is a polynomial of degree n mu plus 1. Therefore, this will be integral a to b wx Pn minus 1 x comma some polynomial, so g of x, which has degree mu plus 1 dx. Is it clear? So g mu plus 1 x is equal to x times p mu x, p mu x. Okay, now let us continue from here. There's no comma here. Just a minute. So when I continue from here, what you will see is that this is equal to plus mu plus 1 is equal to n minus 1 or n, right? Because if mu plus 1 is n, Pn minus 1 x is not orthogonal to polynomials of degree greater than n minus 1. So that won't be 0. But on the other hand, if mu plus 1 is a polynomial of degree n minus 1, then this quantity will be non-zero. Okay, so this is very simple because Pn minus 1x is orthogonal to all polynomials less than n minus 1. So mu can only be, or rather alpha mu can only be non-zero for n mu equal to n minus 1, or rather mu equal to n minus 2 or mu equal to n minus 1. Okay, is this clear? All that I have done is want to evaluate what is alpha mu. So alpha mu is given by fx comma p mu, and I have just expanded fx, which is pn minus 1 kn upon kn minus 1 x pn minus 1 x comma p mu, but mu only goes from 0 to n minus 1. Because of that, the first term pn x p mu is 0, and the second term minus kn upon kn minus 1 x pn minus 1 of x comma p mu, that part will be non-zero only for mu is equal to n minus 2 or n minus 1. So what we get is the following. Pnx minus Kn minus 1 upon Kn x Pn minus 1 x is equal to some alpha n minus 1 Pn minus 1 x plus alpha n minus 2 Pn minus 2 x. Any questions so far? Do you have any doubt? It looks like you people are not there, so I might as well log out.
No, sir.
It's not responding. So why? What takes you so long to respond? Is it clear?
Yes, sir.
So I'll proceed.
Yes.
Okay. So what I have is, so I can write down x now I can write so Pnx, I can write Pnx the following is equal to k minus 1 and x plus alpha n minus 1 minus 1 x plus alpha n minus 2 Pn minus 2 of x. So all I did was take this part to the right hand side, and I've just taken Pn minus 1 as a common factor. Now I want to get alpha n minus 1, n minus 2. To get alpha n, we take inner product on both sides. Pn minus. Okay. So what do I get? Pnx Pn minus 2x is equal to Kn minus 1 should have been a bit careful here. Is equal to Kn minus 1 upon Kn x Pn minus 1 plus phi minus 1 P n minus 1 x comma P n minus 2 x. Okay. So this will be in bracket because I've just had it in bracket. So plus alpha n minus 2 P n minus 2 comma P n minus 2. See, what I have done is very simple. I have taken inner product of the left hand side with both the sides, left and right hand sides with Pn minus 2. So the right hand side inner product will be, the first term will be x Pn minus 1 x comma Pn minus 2. Second one will be alpha n minus 1 Pn minus 1 x comma Pn minus 2. Third one is alpha n minus 2 Pn minus 2 x Pn minus 2 x. Suppose the then Pn minus 2x comma Pn minus 2x inner product is equal to 1. Okay, and then Pn minus 1x Pn minus 2x, this inner product is equal to 0. Okay, so what I'll get, and the left hand side is also 0. So this is also 0 because Pnx comma Pn minus 2x is also 0. So I have 0 equal to Kn minus 1 upon Kn x n minus 1 x comma Pn minus 2 x plus alpha n minus 2. Is it clear? Okay? Is it okay? Is it okay?
Yes, sir.
Okay, so I can now expand it 0 kn minus 1 upon kn times, let me write it as an integral Pn minus 1x a to b x Pn minus 2x wx dx plus alpha n minus 2. Okay, so what I have done is just write it in an integral fashion. So what do I get? I get this to be equal to kn minus 1 integral a to b, okay, of Pn minus 1x times x into kn minus 2. Let me get the whole explicit. Kn minus 2 x to the power n minus 2 plus various things x to the n minus 3 and so forth until the constant wx dx plus alpha n minus 2. Okay, or I can write as k. Okay, and I also divide by kn minus 2. I'm going to divide it by kn minus 1 again. Multiply it by I have divided by kn minus 2 and multiply it by k. Once again, let me. I have to make this one as kn minus 1 x to the power kn minus 1. So it's already I have x to the n minus 1. I have kn minus 2 there. So if I divide the right hand side by kn minus 2, okay, and multiply the up by kn minus 1. Okay, then I will get integral a to b Pn minus 1x into kn minus 1 x to the power n minus 1 plus that times wx dx plus alpha n minus 2. Okay, any questions? Because all I have done is divide by kn minus 2 and multiply by kn minus 1 so that I get the leading term to be that and I don't care for the others. So this leading term that I have, I can write it in the following. Kn into Pn into integral a to b Pn minus 1x into Pn minus 1x will be the first one. So when I can write this to be Pn minus 1x plus sigma over some r equal to 0 to n minus 2. Okay, some c of r, p of, let me also not forget p. I don't need that. I'll write it as c of r x to the power r.
Sir, in the previous equation, why is the coefficient of
wx
to the power n minus 2?
x plus alpha. So on. What's it?
Sir, in the previous equation, why is the
No, it is
of x to the power n minus 1 k n minus 1?
okay. That's because see, look at the following. What I have is kn minus 2 x to the power n minus 2 right here. Okay, I multiply by x, I get kn minus 2 x to the power n minus 1. Okay, and some junk, x to the power n minus 3, x to the power n minus 4, etc. up to constant. Okay, then what I will do is that I will divide this by n minus kn minus 2 and multiply by kn minus 1. Okay, that's what I have done. I have divided this entire expression by kn minus 2 and multiplied by kn minus 1. Then I'll get kn minus 1 x to n minus 1 plus lot of lower powers of x with some coefficient. Right?
Okay, sir, got it, got it.
Okay, then I can write this one as Pn minus 1x plus everything of lower power of x r equal to 0 to n minus 1. Is it okay?
Yes, sir, yes, sir.
Okay. Then what I get is this one. If I'm using normalized, this will be Kn times this part integration will give me plus 0 because Pn less than n minus 1. Okay, so this part will give me 0. This part will give me 1. This part will give me 0. Okay, and the other one will remain as such, alpha n minus 2. So I get alpha n minus 2 is equal to minus of k n minus 1 square upon k n minus 2. Okay, so we have to get alpha n minus 2. Okay, so now let us go back to my old expression, which was here. Alpha n minus 1 phi n minus 1 x. Okay, so I can write this one in the following form. I can write phi n x minus 1 x is equal to I had some alpha n minus 1 pn minus 1 x, okay, plus alpha n minus 2. Okay, so the alpha n minus 2 will be minus of kn minus 1 square upon kn into kn minus 2 times pn minus 2x. Okay, so I've just used alpha n here. Okay, so this alpha n minus 2 that I had is what I have replaced it by. Okay, or here that I had alpha n minus 2. Okay, you can look at it this way. Okay, so now what I can say is that I can rearrange algebraically the whole, write it in the following form. I'll write Pnx is equal to k times x plus some constant, some alpha n minus pn minus 1 x. Okay, and kn minus 1 upon kn into kn minus 2 pn minus 2x. Okay, so okay, or I can always write it in the form slightly different, which is x pn. Okay, is it I will multiply the whole thing by kn, take it to the left hand side, multiply by kn minus 1 by kn. So I will get kn minus 1 by kn pnx, and then when I multiply by kn and this part gets divided by kn minus 1 by kn. Okay. So I can say that plus some beta n minus 1 pn minus 1x, okay, plus kn by 1 by kn minus 2. Okay, so what I did was take this to the left hand side, the right hand side. I said x pn minus 1 is equal to minus of pn minus 1 x, or rather pn x. Okay, this minus pnx came there, and then I had and this multiplied by kn minus 1 outside. Okay, minus plus alpha n minus 1 n minus 1 x minus of kn minus 1 squared by kn minus 2 3n minus 2x. Okay, so this is what I did. I took the kn upon kn minus 1 x times pn minus 1 to the left hand side, and took pnx to the right hand side. I've written down the expanded form. So now you see that if I were to multiply kn minus 1 x, so let me pick that into minus kn minus 1 upon kn is equal to plus kn minus 1 upon kn pnx, because I am multiplying both sides, plus pn minus 1 pn minus x, and then I have plus kn minus 1 upon kn minus 2 pn minus 2x. Now this part I think I have written ulta. Nobody corrected me. So what this should have been was kn upon kn minus 2 upon kn minus 1 squared. This should have been the thing that I should have actually put. So, yeah, you see alpha n minus 2 is k squared n minus 1 upon kn minus. I made a mistake. Okay. So now what you will see is the following. You get a which tells me that plus xpn minus is equal to kn minus 1 upon kn pnx plus beta n minus 1 pn minus 1x plus kn minus 1 upon kn minus 2 pn minus 2x normalized orthogonal polynomial. I have intentionally written down normalized, especially this will have a slightly different form. If it is not normalized, it can be some constant, but you will always have a three-term recurrence relation. So this is known as the three-term recurrence of orthogonal polynomial. Has anyone come across this kind of three-term recurrence relationship?
No, sir.
Have you come across this anywhere? Have you done harmonic oscillator problems?
Sir, the wave function maybe requires this kind of expression for simple harmonic quantum.
When you have a quantum harmonic oscillator and you want to find out the transition dipole between states, okay, then you have to expand, say, wave function of state n with x and state wave function of state n plus m, right? So you will see that because of the three-term recurrence relationship, okay, you can only excite a state from n to either n plus 1 or de-excited to n minus 1. You cannot have anything different. This is the one that gives you, for harmonic oscillators, the selection rule that delta V is equal to plus minus 1. Okay, so
Hermite polynomials.
yeah, for Hermite polynomials you can show. For Hermite polynomials you can show this recurrence relationship 2x hn minus 1 hn plus hn. It is a recurrence relationship for Hermite polynomial.
Okay, sir.
It is 2x. So it's actually there is a is 2. There is a factor. Okay. So this way you will use it. Okay, but there are some. So I can write down, for example, take n equal to 1. So what I get is xp naught is equal to n equal to 1. So this will be k0 upon k1 v1x plus beta 0. Okay, and because we are not going to be having any polynomial n minus 2 for n equal to 1, the term kn minus 1 upon kn minus 2 will be 0. Okay. k1x is equal to k1 upon k2 2x plus p1x plus k2 upon what's the relationship here?
So why the third term should be 0?
When n is equal to 1, okay, how much is n minus 2?
-1.
And we are only looking at polynomials which have got positive powers of x, right? Because we've only dealt with moments matrix corresponding to 1x, x squared, x cubed, etc.
Yes, sir.
Okay. So
Sir, it does not exist, but it how it can be 0?
yeah, if it does not exist, then it is 0.
Okay.
So this one will be k1 upon k2, and the next one will be kn minus 1 upon kn minus 2. That is k1 upon k0, right? N is equal to 2. This is n equal to 2. N equal to 2. This will be k1 upon k0. P0. Okay. And so on and so forth. Right? For n, Pn minus 1x is equal to kn minus 1 upon. It's not writing. P n plus Pn minus 1x plus kn minus 2, kn minus 1. P n minus 2 of x. So I have a whole set of equations. Okay, so I can write down this whole set of as matrix equations, right? So how can I write down this as a matrix equation? I will define a vector which is, let me call it P naught P n minus 1. So this is one vector, right? So what I can do is, if I have this as the vector, then I can write down x P n minus 1 is equal to k naught by k1 0 0 0, and then I have k naught by k1 beta 1 k1 by k2 0, and then I have 0 k1 by k2 beta 2, and then I have k2 by k3 0, etc., 0, etc., and then I have k n minus 1, k n minus 2, no, k n, sorry, k n minus 1 upon k n minus 2 times, and then the next one will be beta n minus 1 times, let me write down this one, p naught p1, I'll draw a variable inside, pn minus 1 plus, I can have all the, and then kn minus 1 upon kn times pn. I can write it in this fashion. Is it clear, or you want me to expand on it?
Yes.
All you have is, supposing you take the final equation, right? If you take the final vector, actually, let me write the full thing. Okay. So if you want the last equation will be x that pn minus 1 is equal to kn minus 1 upon kn minus 2 times p n minus 2, okay, plus beta n minus 1 p n minus 1, plus the last one will be, last component I should add kn minus 1 upon kn times pn, right? Look at any other equation, because all these are zeros. This part that I am looking at only adds to the last equation. So this part I have, it only adds to the last equation. For all the other equations, 0. Okay, because you have a k n plus 1 coming on the right hand side, kn coming on the right hand. Okay, for example, you look at this equation, you have k naught upon k1 phi naught plus beta 1 phi 1 plus k1 by k2 phi 2. Okay, and that happens until phi n minus 1, but Pn minus 2, but when you come to Pn minus 1, you have to add a separate vector which has all 0 components except for the last one, which is Kn minus 1 upon Kn Pn. Okay, any questions? Any questions thus far?
No, sir.
So it's clear? So I can actually. Oops. So I can write it as. I can write it as x vector is equal to vector j times the vector plus the following way. En times Kn minus 1 upon Kn Pn of x. Because En is a vector which will only have, because see the following. E1 is vector. E1 will be 1, 0, E2 is equal to 0, 1, 0, 0, etc., etc. And then I'll have En is equal to everything 0 except the last one. Okay. So if I multiply by this vector, I will get the following. So these are all vectors. Okay. So I can write it as a matrix equation. Okay. What kind of a matrix is J? Look at this matrix J. What kind of a matrix is J? What is the property of the matrices that you know? What are the matrices you know? Can you see anything about the matrix? Is it a unitary matrix? Is it a real matrix? And you people have left, so let me log out. Nobody is. Are you hearing me or you're not hearing? You know, either you know or you don't know. You can answer either way because I'm not able to see you people. So
Sir, I don't
if you are
know.
not going to answer, let me know. That's better. You don't know, no shame. You have to say that. Okay. Is it a real matrix? Look, all the things that you are integrating, okay, are the coefficients are all real because I said that these are all real orthogonal polynomials. Okay, because the functions that we are looking at f of x were all real. So because of that, these are real orthogonal polynomials. Okay, so all the functions are real. Because of that, all beta naught, beta 1, k naught, k1, k2, everything is real. Now, what is the symmetry of the matrix?
So it's equal to its transpose.
So it is a real symmetric matrix. Okay, and what can you say about the eigenvalues of a real symmetric matrix?
They will be real.
Yeah. So let me look at the following. X cube b is 0. Okay. Then what happens? I'll get x cube b n minus 1 x mu is equal to j times p n minus 1 x mu plus what happens to the last term? What is xn mu? Xn of x mu if x mu is the 0 of xn?
0.
Yeah. Okay. So zeros of are eigenvalues of the matrix K. So you take n minus 1 mu equal to x mu pn minus 1 x mu, right? And this shows because all its eigenvalues are real. So this is another proof, or this is another proof for the zeros of the phi and x, zeros of phi and x are all real. See, it's a beautiful proof just starting from the three-term recurrence relationship. So using the three-term recurrence relationship, what we have shown is that the zeros of any orthogonal polynomial are all real. Okay, and you can also get the orthogonal. How do you get bounds? How do you get bounds on the eigenvalues of matrix? What was the theorem that used the zeros of the bounds of the eigenvalues of matrix? What was the theorem we used? Did we study the bounds of the matrix?
Yes, sir, you are done one regarding the bound.
That is given by what is called Kirchgordin's theorem or Hadamard's theorem.
Yes.
Okay, so you can use that theorem and then show where the zeros of an orthogonal polynomial should lie. Okay, and so the limits are known. Okay, so this matrix J is extremely helpful in that case. Okay, now I will go into something else. As an identity known as a to start with, so let me whenever we use the vector E, okay, it has n components. Okay, I'm not going to specify any time later that n. So I have x times p of x, the vector, is equal to j times p of x, the vector, plus kn minus 1 upon kn, p and x times the vector en. Right? Now what I can do is, I can write the same thing for a, instead of having a variable x, I can write it for y. Okay, so I will have y, p of y. It is just, writing the same thing, but it's a childish thing in a way, because I have only done it for, instead of calling the variable x, I'm calling the variable y, but you'll see why. Okay, so now what I'll do is, I'll take the inner product of the top with py with pa. Okay, so when I take the inner product, I get p of y comma x p of y is equal to p of y j p of x plus kn minus 1 upon kn pnx pny. So the en dot en will be 1. Okay, so pn minus 1 y. Sorry. Because py has nth component of py, the vector is pn minus 1y. Okay, so that is why you get pnx pn minus. And similarly, if I take the other one, is equal to
Sir, in the previous equation, on the right hand side, capital phi of y times j times capital phi of x, y is it? Should be capital phi of y.
no, you are talking about this equation
Yeah, the previous equation, sir.
and this term.
Yes, sir. Capital phi of y.
See, I'm taking inner product with p of y, right?
Yes, sir.
So j times p of x is a vector.
Yes.
So I can take the inner product this way. If you want, I can put a comma if you want.
Okay, okay, okay.
Okay, I use a matrix notation and I just left it without a comma. Okay, so is it clear now?
Yes, sir.
Okay, so let's so what happens? Py transpose JPX and px transpose JPy. What can you say about these two? Are they the same? Are they equal?
If J is Hermitian, then they are equal.
J is, yeah, J is real symmetric, so they are equal. J is real symmetric, so they are equal. So I can subtract one from the other. Okay, so everything is real, right? So just a minute. This one should have been y, because I was writing it for y field. So what I will get is the following. If subtract lower equation from upper equation. This is the lower equation. This is the upper equation, subtract, then these two will vanish because the first term will be the same in both cases, right? And what remains is only the left hand side and the last term on the right hand side. So what I'll get is the following. X minus y. Px comma phy, because both of them are px comma phy equal to phy comma phi. Okay, so I can take it as a common factor is equal to pn comma e, right? So what I will get is so kn minus 1 upon k minus kn minus 1 upon k. Into pn on y n y times pn minus x. Correct? What is the left hand side equal to? This is x minus y times sigma over y is equal to k minus 1 of pix gamma pix. Okay, so px comma phi y. So when I take the inner product, it's nothing but product of it. Yes, sir. This is equal to kn minus 1 upon kn. Kn minus 1 times pnx minus half py times pn minus 1 x. So this is of identity. It is extremely useful, and I'll tell you why. So now I can also do something more. I can just play around with it and write it as I is equal to 0 to n minus 1 pix piy is equal to kn minus 1 upon kn times pn minus 1 y pnx minus pn y pn minus 1 x divided by x minus y. And the right hand side is equal to kn minus 1 upon kn. I can write it as pnx times pn y pn minus 1 x divided by x minus y plus pn sorry, just let me let me not rush. Then I can take phi n minus 1x into phi n minus 1x. I've subtracted, I have to add that. So which means it should come on the other side. So I'll have phi n y minus of phi n x divided by x minus y. What I have subtracted phi n minus 1x, phi n x, and added phi n minus 1x, phi n x. So nothing I have changed. Okay. Now I take limit x. Okay, we take limit x tending to y. The left hand side becomes over I equal to 0 to pi x squared is equal to k of n. What can you say about limit x tending to y, phi n minus 1, y minus phi n minus 1 x divided by x minus y? This is
0.
minus of phi n x. Is it 0? What's the basic calculus definition of a derivative? What is the definition of a derivative?
Yes, sir.
F of x plus delta x minus f of x divided by delta x, isn't it?
Yes.
Take x plus delta x to be y and x itself. So what you will get is a derivative. So this minus p n x, p n minus 1 prime y. Plus x into p n prime. It's not y, but it is x only because I'm taking x tending to y. Okay, so supposing I have the zero. Okay, if x's are evaluated at zeros of the polynomial p and x, what happens? Say x mu evaluated at zeros, x mu of the polynomial. What do I get? Sigma over I 0 to n minus 1 pi x mu the whole square is equal to kn minus 1 upon kn. So what is the value of phi n x at phi n x mu? When x equal to x mu, what is the value of phi n x?
0.
Yeah, because x mu is a 0, right? So the first term goes to 0, only the second term remains. So I have pn minus 1 x mu pn prime x. Okay, this is very important in what is called Gauss quadrature. For accurate numerical of integrals. Okay, so now let me come what is called, and you can also show, for example, if you can use the same equation and if you want, you can have a slightly different form of this. So slightly different form of the following. We can show using the recurrence relationship. So I is equal to 0 to n minus 1. Where we can also write equal to kn upon k plus 1 times Pn plus 1x and Pn prime. Okay, so this you can actually work out, and the steps for working out are actually given in Wilf's book on mathematics, and I'm not going to do it. It's fairly straightforward. If you know the recurrence relationship, you can replace kn minus 1 upon kn, Pn minus 1, x mu by this quantity, Pn plus 1 x mu and the kn by kn. Okay, so okay, now let's develop closed quadrature. Okay. So how does one effective integral 0 to 1 f of x dx? So I want to perform this numerically. Okay, so I mean you can always scale the interval instead of 0 to a1, you can say a plus a to b. Okay, it doesn't matter. So how does one do numerically? So you divide the interval n equal subinterval. So you have 0 to 1. Okay, that n intervals, 1. So this, let me call the 0, 1, 2, etc. So I have to put n plus 1 parts, and the at any point x of equal to nu by n. Right? When nu is equal to 0, x0 is 0. Okay. When nu is equal to n, xn is equal to 1. And in between you have x nu equal to nu by n. Okay. Now let us see how. So whenever you want to integrate it, you have various kinds of formulas. So we can integrate the 2-point formula. Okay. What you will do is the following. That is, I have 0 and 1. Okay. And I'll write integral 1 to 1 equal to 1 of f of 0 plus f of 1 into 1. Okay, so I have a function if I want to get. Okay, so I'll take the values of the functions. This is f of 1. This one is f of 0. Okay, I take the average of these two values. Okay, and then multiply by the width of the interval, and so that I get the approximate rectangle, and rectangle the area is nothing but half of f0 plus f1 into 1, and of course this has errors. Okay. So, we use more points. Between 0 and 1. For example, I can have the following. Integral 0 to 1 fx dx is equal to, I have so 1/6 f0. I'll tell you how we can get these formulas. Okay? Plus 2/3 1/2 f plus 1/6 f1. Okay, So this is the Simpson's rule. Okay, where what we have done is the following: 0 to 1. You have taken half, and you have a function like this. Okay, so you treat this as trapezoids at the areas, these trapezoids, and add them up. Okay, in general,
Sir, how the coefficients
So-
are coming f0, f half, f1, 1 by 6, 2 by 3.
I'll tell you how I'm going to get it, and you can work it out. In general, okay, we can. I think this is not the trapezoid rule. This is actually the one. If I have a 2-point formula, okay. So what you have done is, in this case, you formed a trapeze. For the okay. So this is the trapezoid. So the other one is called this. Okay, and in general, we can demand 0 to 1 f of x dx is equal to sigma over mu is equal to 0 to n some weight w nu f of mu by n. Where mu okay, so now is w nu, there are n plus 1 w nu we have to determine. Okay, how do you determine this? You demand the data is accurate, is exact actually for all of degree. Okay, so if you demand that it should be exact for all polynomials of degree n, what you so, so one x for then the formula is exact for any polynomial. What I demand is that if it has to be exact for all polynomials of degree less than or equal to n, I need to demand that it's exact for 1, it's exact for x, it's exact for x squared, all the way to x to the power n. So I have integral 0 to 1 dx is equal to 1 is equal to nu w. Okay, so for the 2-point formula, that's the reason why you will get the sum of the two this thing weights to be 0, to be 1. Then I have 1 x dx is equal to what is the value of 0? Come on.
Half.
Equal to sigma over nu is equal to 0 to n w nu f of x by nu. The f of x by nu in this case will be just x by nu. Nu by n, right? Because that is what the right hand side should be. W nu f of x nu. Okay, so f of x nu is f of nu by n, which is equal to nu by n because f of x is equal to x. Then I have x squared dx. What is equal to? Help me. What is that equal to? Integral 0 to 1 x squared dx.
1/3.
You people want to take all the time in the world so that I cover as little as possible. Nu by n squared. Okay, and like this, I will have x by n dx. What is this equal to? Integral 0 to 1 x to the power n dx.
1 by n. Sorry, 1
1
by
by?
n minus 1.
1 by n minus 1?
Plus 1, sorry, sir.
n plus 1.
Okay, so you know that you have now n equations and n unknowns, right? Or rather n plus n. N plus 1 unknowns, which are W. Okay, so we can solve for W. So we have a quadratic equation. Then have this thing, if for all quadratic polynomials, it is exact for fx equal to 1, x and x squared. Okay, so I get the 1 is equal to W1 plus W2 plus W3. Okay, and half W2 by W2 into 1 by 2 plus W3. Right, because f of x is equal to x. The integral is that this is f of x is equal to so when f of x is equal to 1, you'll get W1 plus W2 plus W3 equal to 1. And when f of x is equal to x, you will get W1 into 0 plus W2 into half plus W3 into 1. Because nu takes the values 0, 1, 2, and x nu takes the values 0 by 2, 0 and 1. 1/3 is equal to x1 is 0, so that won't contribute even because w1 into x1 0 square is 0. 1 second. Hello? World ಬಂದು ಹೋಯ್ತು. Okay, so what we get here is W2 into what is 1/2 squared? 1/4 plus W3 into 1 is equal to 1/3. Right? So what do I get? I get W1 is equal to 1/6. W2 is equal to 2/3. Plus W3. Okay, so this is how you get the formula for what is called ordinary integration. So you get what's called rectangle rule, trapezoidal rule, and then you have the Simpson's rule, and then you can go to higher and higher powers. Okay, but here the problem is the following. That is the numerical. That is, it always uses x nu equal to nu by n. Okay, so the point is that so this leads to only n unknowns or n plus 1 unknown. And hence is accurate only up to polynomials of degree n. That is, I have said that integral 0 to 1 fx dx is equal to sigma over nu is equal to 0 to n w nu f at nu by n. Okay, so this is fixed. Now the thing is that because that is fixed, you only have a n point formula. You see, depend on how many times you have to evaluate the function for a given accuracy. Here you have to evaluate function is evaluated n plus 1 to get accuracy or get exactness, let me say. For okay, supposing I say that if I could keep these nu by n which are fixed, if I choose the points xi, x nu, okay, are such that keeping both x nu and nu, determined. And what happens? You have 2n plus 1 unknowns. We will have two n plus 1 unknowns. Okay, which is which is n plus 1 w new values, n plus 1 x new value. Right? So to determine, we can demand integral 0 to 1 fx dx exactly d1 for all polynomials of degree 2n plus 1. Right? Am I right? See, because what I have got now here is that I have n plus 1 unknown freedom. Okay, so if I can demand that I must get w nu and x nu such that integral 0 to 1 fx dx is equal to this right hand side of the formula is exact for all polynomials of degree 2n plus 1, then I will have because I only evaluate f of x at n points, which is x1, x2 to xn, because x0 I can take to be 0, or maybe say n plus 1 points. So I only need to evaluate function at n plus 1 points, and still I'll get a 2n plus 1 degree polynomial integration exact. Okay, so this is a great advantage if I can do that. But what are the conditions? Real and positive. Okay, because they are the weights. We are weighing a function evaluated at a particular point. You cannot have it. Okay, you can have only weight between 0 and 1. And all should be real and the interval 0, 1. Okay, so supposing I want to do this, it means that, you know, if I want to say, let us say we want a 2-point formula. One second. Oh, my time is almost getting up. We want to get a 2-point formula. Then we will have then W1, W2, and X1, X2. So you will set up 4 equations, and so 2-point up to 2n plus 1, which is in my case it will be 5, degree 5. Okay, Actually, I have 4 unknowns, so I'll have to write down 4 equations, which means that it should be correct to 2n minus 1, because x equal to 0 I did not consider in the previous discussion. Okay, so we will see how we can do this by using Gauss quadrature technique. So the main condition is that the weight W nu should be greater than 0. All the x nu's must lie in the interval 0 to 1, and they should all be real. Otherwise, this formula won't work. Okay, because integral of a real function is always real. Okay, a definite integral of a real function is always a real number, and also you are going to evaluate the function only between the intervals which you are integrating it, and the weights should be positive. So let's see how we can do this, and we will discuss. But this is one of the really important. Okay, so till then we'll meet Monday again. Until then, you can probably look up some of these things, read it, and be ready for the next class. Thank you. Any questions?
No, sir.
Okay, so we'll stop here.